We started class today by having you look at all the different factor pairs for 24, and what you were trying to find is some patterns. So some of you wrote down 1 times 24, and some of you put down 2 times 12, and some said 3 times 8, and some said 4 times 6. And then I asked you what they all have in common besides multiplying to 24. And we talked about a lot of patterns in class, but what we eventually did is we broke each of these factors into their prime factors. That's called prime factorization. So if I start with 4 times 6, I can break 4 into 2 times 2 because 2 times 2 is 4, and I can break 6 into 2 times 3 because 2 times 3 is 6. But I can't break these down into anything else because 1 won't change anything. And now I just check. 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is 24. So I know that the prime factors that multiply to 24, even when I start with 4 times 6, are 2 times 2 times 2 times 3. If we start with 2 times 12, 2 is a prime number all by itself. We break 12 into 3 times 4. 3 is a prime number. We break 4 into 2 times 2. And notice we have the same numbers. They're in a different order, but we have the same numbers. 2 times 2 times 2 times 3. And if we start, some of you that wrote down 3 times 8, 3 is a prime number. We broke 8 into 2 times 4, 2 is prime, and we broke 4 into 2 times 2. Notice once again, even though we began with a different factor pair, we end up with the same set of primes. 2 times 2 times 2 times 3. So that's what we're studying today. All right, so it's kind of cool in that the most fundamental theorem of arithmetic is that every number, every counting number, is either a prime number or it has only one set of prime factors. So if we look at 24, there's only one set of prime numbers that multiply to 24, and that is 2 times 2 times 2 times 3. We can also call this 2 cubed times 3. 2 cubed is 8, 8 times 3 is 24. All of the factor pairs that we started class with today are just combinations of these. If I put these two together and these two together, I get 4 times 6. If I group 2 times 2 together and get 4, 2 times 3, there's a 6. That makes 12. Or I can group these three together, and that's 12, and I have my 2. If I group these two together with these, 2 times 2 is 4. If I group it with this one, I get 8, and 8 times 3 is 24. So all of these factor pairs are just combinations of the primes that make 24. So just like each of you have a unique fingerprint, 24 has a unique prime factorization, and that is 2 times 2 times 2 times 3. No other prime numbers multiply to 24 other than 2 times 2 times 2 times 3. So prime numbers, they're just a number with two different factors, 1 times itself. But the itself cannot be 1. So they must have two different factors, which is why the number 1 is not a prime number. The smallest prime number is 2. The only way you can get a product of 2 is 1 times 2. 3 is the next prime number. 1 times 3 is 3. And why are they important? Because they're the building blocks of all products. If you understand this whole idea that every number has only one fingerprint of primes, and all of the other factor pairs come from that fingerprint, from those prime numbers in different combinations. So we started off today just with those patterns, but really what we're building are factor trees. So if we start with the number 24, I said, a good idea is just always start with the smallest prime number. If it's an even number, you know it's divisible by 2. So 2 times 12 gives me 24, and it's prime, so I circle it. Think of it as an apple at the end of a tree branch. I'm done with that apple. It's there. 12 I can break into two more primes, two more factors rather, and again I try to use 2 because I know that's prime. 2 times 6, I circle my 2. 6 can be broken again into 2 times 3. 3 is prime, 2 is prime, so I circle them. And that's how I end up getting 2 times 2 times 2 times 3. Always check by multiplying, make sure that this equals 24. And there are no other primes that equal 24. I can rename this as 2 cubed times 3, but that's the same numbers, 2 times 2 times 2 times 3. So to get you to see that when you circle those primes, it's kind of like having the apples on the end of the branches of an apple tree. So what you want to do is pluck all those apples, put them together, and if I multiply them, I get 24. This is called the prime factorization of 24. So remember, there's only one set of primes that equals 24, and those are what those apples represent. Okay, then each group took a different factor pair. So for 30, one group used 6 times 5, and they broke it into primes, and they found that the prime factorization of 30 is 2 times 3 times 5. Another group started with 10 times 3. 3 is prime. They circled, they broke that into 2 times 5, and they get the same prime factorization, 2 times 5 times 3. And another group started with 15 times 2. Circle the 2, break 15 apart into 3 times 5, and they get the same factorization, 2 times 5 times 3. So that's what that fundamental theorem of arithmetic says. Okay, why bother doing this? Well, you can use this idea of breaking numbers into prime factors to help you find the greatest common factor so that you can simplify a fraction to lowest terms. So let's take the fraction 150 2/50ths. You guys know I could divide both of these by 10, and I can divide them both by 5, and I can keep doing that until I get to where these numbers have no other common factors other than 1, which won't change it. But another way to do it is to write out the primes of 150. So I make a factor tree, and they end up with 2 times 3 times 5 times 5 for 150. And I do the same with 250, and I end up with 2 times 5 times 5 times 5. I look and see the matches. This 2 matches this 2, so I put a 2 in my box. This 5 matches this 5, so I put a 5 in my box. This 5 matches this 5, so I put another 5 in my box. I don't put a third 5 in my box because there's no third 5 here. Remember, I'm looking for the ones they have in common. And I can't put a 3 in my box because there's no 3 here. I take those numbers that are in my box and you multiply them together because these are the common primes for these two numbers. And when you multiply them together, you get 50, which tells you that the greatest common factor of 150 and 250 is 50. So if I want to simplify them to lowest terms in one quick step, I divide 150 by 50, I divide 250 by 50, and there's my fraction in lowest terms. You can also see it. What's the only thing left? If I take out 50 as a factor, I'm left with 3 on top. If I take out 50 as a factor for 250, I'm left with 5 on the bottom. Do you see the fraction? 3/5 right here? 3/5. There's the answer in lowest terms because I'm taking out these 3 factors because they multiply to 50. That's the same thing as dividing by 50. All right. Then the words relatively prime, just make sure you know what these mean. Okay, when two numbers have no other common factors other than 1, they're called relatively prime. So I cannot find any common factor for 3 and 5 except for the number 1. And that won't change it. If I divide them each by 1, I get 3/5 again. So when you cannot simplify the fraction anymore when the numerator and denominator are relatively prime. Now, you don't have to have prime numbers to have them relatively prime. 4/9, 4 is not a prime number because it's even. It's got 2 times 2 and 1 times 4. 9 is not a prime number. I can multiply 1 times 9 and 3 times 3. But 4 and 9 have no common factors other than 1. So 4 and 9 are relatively prime. You have to have two numbers to have a relationship of relatively prime. So think of like if your parents have no siblings, then you can't have a cousin because it takes two people to have cousins who are relatives. Same thing here. It takes two numbers and their common factor to be relatively prime can only be 1. So the numbers themselves aren't prime, it's the relationship between the two numbers. So then we tried this process. So I gave you the primes of 250, and then you guys did a factor tree to come up with the primes of 120, which is 2 times 2 times 2 times 3 times 5. We looked at the ones that they have in common. There's a 2 here and a 2 here. Throw it in the box. There's no other 2's down here and no 3's, but this 5 matches a 5 here, so I put it in the box. I multiply them, and 10 is my greatest common factor. So I can divide 120 by 10 and 250 by 10, and I get the lowest terms for this fraction is 12/25. And 12 and 25, while they're not prime numbers themselves, 12 and 25 are relatively prime. I can divide 25 by 5, but I cannot divide 12 by 5. I can divide 12 by 2, 3, 4, and 6, but I cannot divide 25 by any of those numbers. So the only common factor they have is the number 1.
So that's why they're relatively prime and it's in lowest terms. All right, make sure you check your blog, read my comments on your project, read my comments on your blog post. They're all graded. I've given you all feedback. I used Rochelle. She did an awesome job on her paragraph. So I wanted you guys all to know that I talked to Mrs. Foxall today, and she said that she and Mr. Gonzalez do use these same words. A well-written paragraph has a topic sentence and a concluding sentence, and they say almost the same thing. And then your three examples need to have transition words. So for the essential question for chapter 2, notice that Rochelle used transition words. First, you can use variables to represent unknown quantities, and then she has an example from her book to solve a problem when she's looking for an unknown. Next, transition word, you can use variables to illustrate patterns, and then she has an example from her book that shows doing that to solve a problem. And last, you can use variables in formulas. A transition word, first, next, last. And then she gives an example of the Pythagorean theorem being a formula. And then she has her concluding sentence. So just kind of compare what you did and see where you're missing the boat on writing a well-constructed paragraph. Okay, we're going to continue. All of you did 1 through 10. Now you can decide whether you want to finish this practice by doing the basic or the challenge, and then read the choices on pages 194 to 195 for your next project, and you're going to have to make a decision about which one you want to do by next class. I'm going to ask you to commit because all of them involve a little bit of research. And the rest of the